Right now, as you watch this video, there is a blind spot in your eye. Not metaphorically, literally. A region of your retina where you cannot see anything at all. No color, no light, no movement, just nothing. And here's what gets me. You have no idea it's there. Your brain is quietly filling it in, patching over the gap like a photo editing tool, making you believe you have complete, seamless vision. You don't. And that's just the eye. We haven't even gotten started. I'm a physician. I spend my days studying the human body in extraordinary detail. And the more I learn, the more I find myself asking the same question an engineer would ask when reviewing a design. Who approved this? Welcome to the Engineering Doctor, where we look at the human body not with reverence, but with curiosity. With the kind of fascinated, slightly horrified curiosity of someone who just opened the hood of a car and found the engine held together with rubber bands. The human body is remarkable, genuinely. It does things no machine we've ever built can fully replicate. But it also has some truly baffling design decisions, flaws that an engineer would flag immediately, redundancies that don't exist where they should, single points of failure that seem almost reckless. Today, we're going through 5 of them, and I promise, by the end of this video, you will never look at your own body the same way again. Let's start with the eye. The human eye is often cited as a marvel of biological engineering, and in many ways it is. It can detect a single photon of light, adjust to conditions ranging from bright sunlight to near total darkness, and track fast-moving objects with extraordinary precision. But there's a problem, a fundamental structural problem that any optical engineer would have caught on day one. The photoreceptors in your retina, the cells that actually detect light, are pointing the wrong way. I want you to think about that for a moment. The cells responsible for capturing visual information are facing away from the incoming light. The wiring, the nerve fibers that carry the signal to the brain, runs in front of the photoreceptors, between them and the light source. And all of that wiring has to exit the eye somewhere, so it bundles together and punches a hole straight through the retina. That hole is your optic disc, and at your optic disc, there are 0 photoreceptors. None. That's your blind spot. Here's a fascinating detail. The cephalopod eye, the eye of an octopus or squid, doesn't have this problem. Their photoreceptors face the right direction. Their wiring exits from behind. No blind spot. An octopus has better eye architecture than you do. Your brain compensates, of course. It's extraordinarily good at filling in missing information using context from the surrounding visual field. You'll almost never notice your blind spot in daily life unless you go looking for it. But the compensation doesn't change the underlying design flaw. A good engineer doesn't rely on workarounds to cover for a structural mistake. They fix the structure. The eye didn't get fixed. It just got a very impressive patch job. This one genuinely fascinates me every time I think about it. There is a nerve in your body called the recurrent laryngeal nerve. Its job is to connect your brain to your voice box, your larynx. A simple enough task. The brain is up here, the larynx is right here in your neck. Short distance, straightforward connection. Except that's not what happens. The nerve leaves your brain, travels down your neck, loops all the way down into your chest, wraps around your aorta, the largest artery in your body, and then travels back up to reach the larynx. In humans, this detour adds a few inches, inconvenient but manageable. In a giraffe, this same nerve, doing the exact same job, connecting brain to larynx, travels 15 feet out of its way. 15 feet. down the entire length of that neck and back up again. No engineer designing a communication cable would ever route it this way. You run the cable the shortest distance between 2 points. You don't loop it around major infrastructure and double back. The reason this happens comes down to evolutionary history. Our fish ancestors had a simpler body plan. The nerve, the heart, and the gills were all roughly level. As necks developed and hearts descended into the chest, the nerve got trapped. It couldn't cross the aorta, so it went around. And it's been going around ever since. Evolution doesn't redesign from scratch. It works with what it has. An engineer gets a clean slate. We did not get a clean slate. The spine is a load-bearing column. Its job is to support the weight of your upper body, protect the spinal cord, and allow flexible movement in multiple directions. By those criteria, it is a genuinely impressive structure. 33 vertebrae, intervertebral discs acting as shock absorbers, an elegant S-curve that distributes load efficiently. Here's the problem. It was never designed for what we're asking it to do. The human spine evolved in ancestors who walked on 4 limbs. The spine was oriented horizontally, like a suspension bridge, with the weight distributed along its length. That works beautifully. Then we stood up, and suddenly we took a horizontal load-bearing structure and oriented it vertically. We asked a suspension bridge to become a skyscraper. The S-curve helps. It's an adaptation that distributes the compressive load better than a straight vertical column would. But it's a modification, an adjustment to an existing design, not an original solution to the problem of upright locomotion. The result is predictable. Lower back pain affects up to 80% of people at some point in their lives. It is one of the leading causes of disability worldwide. Herniated discs, spinal stenosis, sciatica, these are not rare anomalies. They are near universal consequences of asking a spine to do something it wasn't originally built for. An engineer tasked with designing a bipedal load-bearing structure from scratch would not produce the human spine. They would build something fundamentally different, something with the vertical orientation baked in from the start. Instead, we got a retrofit, and we've been paying for it ever since. I'll be brief here because the appendix has been mocked enough, but it belongs on this list. The appendix is a small, finger-shaped pouch attached to your large intestine. In some of our ancestors, it likely played a role in digesting tough plant material, housing bacteria that helped break down cellulose. As our diet changed, this function became largely obsolete. The appendix shrank, and now we have a vestigial structure that serves, at best, a minor immune function, and at worst, becomes inflamed, ruptures, and kills you. Appendicitis affects roughly 5% of people. Before surgical intervention became available, a ruptured appendix was a death sentence. In engineering terms, this is a deprecated component that was never properly decommissioned. It's still drawing resources, still occupying space, and still capable of catastrophic failure. Any responsible engineer doing a design review would flag this immediately, remove it, or replace it with something useful. We kept it. It occasionally tries to kill us. We surgically remove it when it does. That is not a good system. I've saved what might be the most baffling decision for last. Your airway and your food passage share a common opening at the back of your throat. Think about the engineering implications of this for a moment. You have 2 critical systems, respiratory and digestive, that must operate continuously in close coordination through the same physical channel. Every time you swallow, a small flap called the epiglottis has to close over your airway to prevent food from entering your lungs. This works the vast majority of the time. The epiglottis is fast and reliable, but not always. Choking is the fourth leading cause of accidental death in the United States. It kills thousands of people every year. Aspiration pneumonia, caused by food or liquid entering the lungs, is a leading cause of death in elderly and neurologically impaired patients. These are not freak accidents. They are predictable failure modes of a system that routes two incompatible functions through the same pipe. No engineer designing a life support system from scratch would make this choice. You separate critical systems. You give breathing its own dedicated channel. You do not put a single flap between a person and asphyxiation. Fish breathe through gills. Their respiratory and digestive systems are completely separate. As our aquatic ancestors transitioned to land, the two systems converged, and they've been sharing that awkward crossroads ever since. Again, evolution retrofitting, not redesigning. So here's where I land after going through all of this. The human body is extraordinary. The more you study it, the more you appreciate the sheer complexity of what it does. Billions of processes running simultaneously, self-repairing, self-regulating, adapting to an enormous range of conditions. But it is not optimally designed. It is historically designed. Every flaw we've looked at today isn't random. It's a remnant, a trace of where we came from, a constraint that evolution couldn't fully escape because it can only modify what already exists. An engineer gets to start fresh. Evolution never does. And I find that genuinely fascinating. Not frustrating, fascinating, because every design flaw in the human body is also a window into our history, a clue about what we used to be. That's what this channel is about. Looking at the body the way an engineer would, with curiosity, with rigor, with a willingness to ask uncomfortable questions, and seeing what we find. Next time, we're going to look at the heart, specifically, why, by engineering standards, it is a deeply questionable pump. If that sounds interesting to you, subscribe, because we're just getting started.